If you go into a really high-end cafe right now, the barista behind the counter will probably tell you that making coffee is, an art form.
Oh, absolutely. It's a whole performance.
Right. You watch them work, and it looks incredibly precise. I mean, they rely on their feel for the beans, their intuition for the grind, and they're constantly staring at these highly sensitive digital temperature probes.
Yeah, it all feels so incredibly controlled.
But what if I told you that every single one of those digital probes is actively lying to them?
I love this because it just shatters the illusion entirely.
It really does. And what if the traditional brewing methods you use in your kitchen every single morning, whether that's a French press, a pour over, or a shiny espresso machine,
hmm
what if they are actually completely chaotic, out of control physical systems?
We really like to believe we are the masters of our morning routine, right? Directing hot water and roasted beans with absolute precision.
Yeah, we feel like scientists in our kitchens.
Exactly. But the moment you look at the actual fluid dynamics and thermodynamics involved, you realize we are, well, practically blindfolded. The coffee we drink is essentially the result of a happy accident in a highly unpredictable environment.
Which is exactly why you are here with us today. So, welcome to the deep dive.
Thanks for having me.
Today, we're taking a fascinating, unapologetically nerdy journey into the absolute bleeding edge of coffee science. So if you've ever stared at your coffee maker in sheer frustration because you use the exact same beans, exact same water, exact same grind, but, Tuesday's cup tasted like heaven and Wednesday's cup tasted like battery acid, this is for you.
It is the ultimate frustration for coffee drinkers.
Truly. We are looking at an incredible stack of sources today, a suite of digital tools, published articles, and complex mechanical models developed by Professor Stephen Abt.
Right, the practical mechanical science guy.
Exactly. He runs a site dedicated to that exact concept, and he has turned his brilliant analytical mind strictly toward the physics and chemistry of roasting and brewing coffee.
And what makes Professor Abbott's approach so refreshing and honestly so disruptive to the coffee industry is that he entirely bypasses the usual barista mysticism.
Yes, there's no listening to the bean here.
Right, no vague romantic concepts about feeling the roast.
Hmm.
We are looking exclusively at the hard, immutable laws of physics. We're talking about things like mass transfer coefficients, the Froude number, Arrhenius activation energies.
Oh, and the mathematical geometry of fractured cellulose.
It's pure physics.
So we're going to take you on a journey from a raw, green coffee bean bouncing around inside a scorching hot roasting drum, all the way to a fundamentally revolutionary chemistry lab-inspired method of brewing called uniform extraction.
A method that really might just change how you make coffee forever.
Okay, let's unpack this. I want to start where the flavor actually begins, which is the roast itself. Because, if the beans aren't roasted right, nothing else matters.
That is the logical starting point. But right out of the gate, Professor Abbott throws a massive wrench into how most of us, and honestly most professional roasters, think about coffee roasting.
How so?
Well, if you talk to a professional roaster, they'll usually show you these beautiful, incredibly intricate graphs of their roast profiles. You've probably seen them if you've ever walked past a commercial roaster.
Yeah, screens with lines going up, dipping down, crossing over each other.
Exactly, tracking temperature down to the decimal point.
Right, it looks like mission control at NASA. And they're usually tracking two main lines on those graphs, right? The environment temperature, which they call ET, and the bean temperature, or BT.
Yeah, that's the industry standard. But Abbott points out a monumental, fundamental flaw in this entire setup. He classifies drum roasting as what physicists mathematically call an ill-posed physical problem.
Wait, an ill-posed problem. I know in mathematics, a well-posed problem is one where a unique solution exists and you have all the necessary data to find it. So an ill-posed problem is basically a mathematician's polite way of saying, you have absolutely no idea what is actually happening in there, and your math is a complete mess.
That is a highly accurate translation, yeah. It means you're trying to calculate a definitive result, the perfect roast, without having nearly enough accurate information to actually solve the equation.
Because the roaster is just too complex.
Exactly. To do a true first principles calculation of what is happening inside a spinning coffee roaster, you would need data points that are simply impossible to measure in real time.
Like what?
Well, you would need to know the exact thermal mass of the changing metal drum. You would need to calculate the Biot number of the heat flow.
Hold on. The Biot number. Let's make sure that makes sense to the listener. That's the ratio of the heat transfer resistance inside the bean versus the heat transferring to its surface, right?
Precisely.
So if the Biot number is high, the outside of the coffee bean is scorching and turning to ash, while the inside core is still, raw and green.
You've got it. And you would need to constantly monitor that biot number for thousands of individual beans simultaneously.
Which is impossible.
Physically impossible. You'd also need to know the precise positions and thermal masses of the metal temperature probes themselves, the complex aerodynamics of the exhaust gases pulling heat out of the drum.
It's just too many moving parts.
Way too many. The localized heat transfer coefficients change every single second as the beans tumble. Nobody has that data. You just can't gather it in a commercial roasting environment.
So if it's an ill-posed problem, what are those mission control screens actually measuring? I mean, if I'm a roaster and I'm staring at the bean temperature, the BT probe, what is that line on the graph telling me?
It is telling you an illusion.
An illusion.
Let's look at the actual mechanics of the B2 probe. You have a heavy, hot metal roasting drum. Sticking into the middle of that drum is a metal thermocouple probe. Before you even put the beans in, the roaster is preheated.
Right, so the probe is sitting in hundreds of degrees of ambient heat.
Exactly. So that metal probe itself is physically very hot. Then you drop room temperature, cold, raw green coffee beans into that scorching hot roaster.
Okay, I'm with you.
What does the BT probe show on the screen? It doesn't start at room temperature. It starts incredibly high because the probe is already hot.
Ah, right. And then all these cold beans crash into it. So the probe isn't actually measuring the beans. The probe is just measuring its own thermal inertia.
Exactly.
It's measuring itself cooling down because cold beans are touching it.
And this leads to one of the greatest myths in coffee roasting. When those cold beans hit the hot probe, the temperature reading on the screen plummets.
It just nosedives.
Right. It drops drastically for a few minutes until it hits a trough, and then the line starts to curve back upward. Roasters universally call this trough the turning point.
And the industry lore is that this is the magical moment when the beans stop cooling the roaster and actually start getting hotter themselves.
That's what everyone says, but logically that violates basic thermodynamics.
I mean, yeah. If you drop a cold coffee bean into a 400-degree oven, it doesn't wait 2 minutes to start getting hotter.
Of course not.
It starts absorbing heat the very millisecond it crosses the threshold.
Exactly. The beans are getting hotter the entire time. The turning point on the graph is a complete fiction.
That is wild.
It's simply the mathematical moment when the rising heat of the coffee beans has finally overcome the cooling thermal inertia of the thick metal probe.
It's like trying to measure the temperature of a Thanksgiving turkey by taking a massive, heady cast iron thermometer, waving it around in the hot oven air until the metal is 400 degrees, and then eventually stabbing it into the freezing cold raw turkey.
That is a perfect analogy.
And then trying to guess the actual internal temperature of the meat based on how fast the heavy metal probe cools down and then eventually heats back up. I mean, it's an indirect, highly misleading illusion.
What's fascinating here is that if we accept that the BT probe is lying to us, and the environment temperature is just a messy, chaotic average of exhaust gases and ambient heat,
we have to ask, what is the actual driving force of the roast?
yes. If we want to look at the hard physics, what metric actually matters?
Well, if it's not the bean temperature and it's not the environment, it has to be the heat source itself, right? The energy being pushed into the system.
Correct. Abbott identifies the true driver of the roast as an incredibly elusive, difficult-to-measure metric called the inlet temperature, or the IT.
Yeah, IT.
This is the temperature of the hot air that is actively being delivered into the roasting drum to heat the beans.
So the air hitting the beans rather than the exhaust air leaving the beans.
Right. If you discount the conductive heat coming straight off the hot metal walls of the drum, which is significant but secondary, it is the IT that is delivering the massive wave of actual thermal energy.
But I'm guessing it's hard to measure.
Notoriously difficult. You can't just stick a single probe in there because air flows into a rotating drum at wildly different rates across its diameter. You have turbulent eddies, stagnant zones.
Right, it's not a uniform wind.
Exactly. But mathematically, when Abbott built his virtual roasting simulation models, the inlet temperature is the core independent variable driving the entire equation.
So Abbott builds this virtual roasting simulator to try and model this ill-posed problem and, find some semblance of control.
Yeah.
And when you look at the parameters he inputs into this software, you start to realize just how many physical variables are actively fighting against the roaster.
Oh, the variables are endless.
You have the bean weight, obviously. More physical mass means you need more thermal energy. But then there's a highly volatile variable, which is moisture percentage.
Yes, and moisture is the variable that makes roasting dynamically complex.
Because the beans aren't dry.
Right. Raw green coffee beans aren't completely dry at all. They have a significant water content, usually around 10 to 12% of their total mass.
Yep.
So in the early stages of the roast, the heat energy flooding into the drum from the inlet temperature isn't just raising the physical temperature of the bean. A massive amount of that thermal energy is being consumed simply to boil and evaporate that water.
It's an endothermic reaction.
Exactly.
The beans are essentially acting as a heat sink. They're sucking heat out of the system without their own internal temperature rising proportionally, purely because the energy is being spent changing water from a liquid state to a gaseous state.
And evaporating water takes a tremendous amount of energy. This heavily retards the rate at which the bean's actual temperature can rise. This is the drying phase of the roast.
Got it.
But here is where the physics gets incredibly tricky and where a lot of roasters lose control. As that water turns to steam and leaves the exhaust system, the physical mass of the bean batch is shrinking in real time.
I see where this is going.
Right.
You have the exact same amount of intense heat energy pouring into the drum from your burners, but suddenly, minute by minute, there's less physical stuff inside the drum to absorb it.
Exactly. The thermal mass is dropping. So naturally, if heat stays constant and mass drops, the rate of the roast begins to aggressively speed up.
Because there's less bean to heat.
Exactly. And it accelerates even more because eventually, as the beans get hot enough, usually around 150 to 160 degrees Celsius, they undergo a fundamental chemical shift. They transition from being endothermic to being exothermic.
Meaning they stop sucking in heat from the burner and they actually start generating their own heat.
Yes. The complex chemical reactions of roasting, the Maillard reactions, the caramelization of sugars, the breakdown of cellulose, these reactions take over.
Right.
The bean is rapidly releasing carbon dioxide, burning off organic cellular structures, and generating its own internal thermal energy.
And this culminates right around what the coffee world calls first crack, right?
That's the one.
If you've ever roasted coffee or even just listened to a roaster, you hear this distinct popping sound, almost like popcorn.
It's very noticeable.
And that is the physical sound of the pressure inside the bean, which builds up to something like 15 or 25 atmospheres of pressure from trapped steam and CO2 literally bursting the cellulose cell walls.
First crack is a violent physical event. Post first crack, the beans are structurally open. The remaining moisture and CO2 are rushing out of the microfractures, the mass is dropping off a cliff, and the beans are generating a massive amount of their own exothermic energy.
Wow.
If the roaster doesn't anticipate this and drastically step down their input heat power, which Abbott measures in megajoules per hour, they will hit a phenomenon the roasting community absolutely dreads. They call it the flick of death.
The flick of death. I mean, it sounds incredibly dramatic, but in a roastery, it really is a disaster.
It is essentially a runaway thermal chain reaction. The temperature suddenly spikes, the mathematical rate of rise curve on the graph shoots violently upward, and your beautifully delicate, carefully nurtured coffee beans are suddenly scorched.
They just burn.
They undergo rapid pyrolysis. They turn to carbon. Your coffee will taste incredibly bitter, like ash and burnt rubber, because you essentially burned them from the inside out. You failed to account for their own exothermic energy contribution to the system.
Okay, so a roaster is trying to manage moisture loss. They're trying to manage real-time mass loss. They're dodging the runaway exothermic flick of death, and all the while, their digital probes are lying to them.
It's a lot to juggle.
And we haven't even talked about the physical mechanics of the machine itself. I mean, this isn't a static oven. The beans are constantly tumbling.
Right.
And Abbott's models get deeply specific about the fluid mechanics of how they tumble. He introduces a concept called the Froude number. That's F-R-O-U-D-E. What exactly is a Froude number?
The Froude number is a dimensionless metric used widely in fluid mechanics and granular mechanics.
Okay.
It's used in everything from calculating water flow over a dam to the mixing of industrial pharmaceutical powders.
So,
In the context of a rotating coffee drum, it represents the mathematical ratio of centrifugal force to gravitational force.
let's visualize that for the listener. Centrifugal force is what pins you to the wall of a spinning carnival ride, like the gravitron.
Right. It wants to push you outward.
And gravity is the downward force that wants to pull you straight to the floor. So the Froude number is the battle between the spin pushing the beans out and gravity pulling the beans down.
Exactly. The actual calculation for a roasting drum involves taking the rotation speed of the drum, measured in radians per second, squared, multiplying that by the physical radius of the drum, and then dividing the whole thing by the constant acceleration of gravity.
Okay, so practically speaking, what happens if my Froude number is completely wrong? Like, what if the drum spins way too fast?
Well, if the centrifugal force is too high, the Froude number goes well above 1.0. The beans just pin themselves flat to the outside metal wall of the drum.
They just stick there.
Exactly. They don't tumble at all. They just ride the wall in a continuous circle, absorbing massive amounts of conductive heat straight from the scorching metal, and they burn instantly.
And if it spins too slowly? If the Froude number is too low?
Then the centrifugal force is too weak, and gravity dominates the system entirely.
Okay.
The beans never travel up the side of the drum. They just slide sluggishly along the very bottom in a massive, dense, impenetrable pile.
That sounds bad.
It is. The hot inlet air can't pass uniformly through a dense pile, so the beans physically touching the bottom metal burn, and the beans sitting on top of the pile stay completely raw.
So you really need a sweet spot.
You do. In granular mechanics, a Froude number slightly below 1.0, often around 0.8 or 0.9, is considered optimal.
Okay, 0.8 or 0.9.
That is the precise mathematical sweet spot where the centrifugal force carries the beans high up the side of the rotating drum, but right before they reach the apex, gravity overtakes the centrifugal force, and the beans cascade beautifully through the open air, right in the path of the hot inlet airflow.
And we still aren't done with the physics of the drum, because the drum isn't just transferring heat through physical contact, and it's not just blowing hot air. There is a third type of heat transfer at play, which is radiative heat transfer. It's like standing 10 feet away from a massive bonfire. You aren't touching the flames, and the air between you and the fire might actually be cold, but you feel intense heat radiating across the gap, hitting your face.
Yes, and Abbott has modeled this radiative heat transfer extensively, relying on the Stefan Boltzmann law.
The Stefan Boltzmann constant.
Right. It dictates that radiative heat transfer is incredibly powerful because it depends on the absolute temperature raised to the fourth power.
Wait, raised to the fourth power. That is massive.
It really is.
That means if the temperature of the drum doubles, the radiative heat it throws off doesn't double. It increases by a factor of 16.
Exactly. It's scaled exponentially. But crucially, radiative heat transfer also depends on a variable called emissivity.
Emissivity.
Emissivity is a dimensionless number between 0 and 1 that measures how efficiently a specific surface emits or absorbs thermal radiation.
Okay, so let's apply emissivity to the physical metal of a coffee roaster. How does that actually change the flavor of the beans?
Think about the inside of the roasting drum. If you buy a brand new roaster, you have a shiny, polished steel drum.
Okay.
That shiny metal might have an emissivity of around 0.15. It acts more like a mirror. It reflects a lot of the thermal energy back, rather than absorbing it and radiating it efficiently into the beans.
Right.
But over months and years of roasting, the inside of that drum gets coated in vaporized coffee oils, carbon, and soot. It becomes blackened and well-seasoned.
And a black surface absorbs and radiates heat much better than a shiny surface.
Significantly better. A well-used blackened drum might see its emissivity jump up to around 0.9. It begins to behave mathematically much more like a theoretical black body radiator.
That is wild.
Isn't it?
That means you could have the exact same roasting machine in the exact same room using the exact same gas pressure and the exact same beans. But the batch you roast on day 1 of owning the machine will taste completely different from the batch you roast on day 1000, purely because the microscopic layer of carbon on the metal changed the emissivity variable in the Stefan Boltzmann equation, throwing way more radiative heat at the beans.
Precisely. And when you stack all of these chaotic variables together, it leads Abbott to a fascinating and frankly highly controversial conclusion within the coffee industry.
Which is?
Well, if drum roasting is an ill-posed mathematical problem,
Right.
if our temperature probes are constantly lying to us due to their own thermal inertia,
Yeah.
if the mass of the beans is constantly dropping and the beans switch from endothermic to exothermic without warning, and the Froude number and drum emissivity are constantly shifting the heat transfer mechanics,
It's a nightmare.
it is. So trying to micromanage a roast by constantly nudging the gas dial up and down based on a misleading line graph is an absolute exercise in futility.
You are basically driving a car blindfolded, and every time you feel a bump, you violently jerk the steering wheel. I mean, it's a miracle we get anything drinkable at all.
Exactly.
So if we can't trust our probes and the system is this chaotic, how on earth are we supposed to roast coffee reliably?
Abbott advocates strongly for a minority opinion in the roasting world called the two-step roasting method.
Two-step. Okay.
The philosophy is simple. Stop fighting the physics. Instead of constantly fiddling with the gas parameters every 30 seconds, you do the complex math up front. You start the roast at a carefully calculated high full power.
Right, to deal with the water.
Yes. This massive wave of thermal energy is designed strictly to overcome that massive endothermic moisture loss phase quickly. And then at one specific mathematically pre-calculated moment, you make one single switch to a lower power setting.
Just one switch for the entire 12-minute roast.
Just one. You drop the power and you let the thermodynamics take over. Abbott's software actually calculates this optimum two-step process for you. It pinpoints exactly what percentage of power you need to drop to, and at exactly what minute and second you need to make the switch, so that the ambient heat perfectly guides the beans through their exothermic first crack without triggering the flick of death.
That's brilliant.
You stop trying to control the chaotic variables manually and let the immutable laws of thermodynamics run their natural course.
That is incredibly elegant. It's like instead of trying to steer a car out of an icy skid by panicking and jerking the wheel back and forth, you just apply the exact right amount of brake, hold the wheel steady, and let the physical momentum of the vehicle correct itself.
Exactly.
Okay, so let's assume we've done the math. We've used our two-step method, we've managed the Froude number, we've accounted for emissivity, and we have a batch of beautifully, perfectly roasted beans. Our job as the controller of variables is done, right? We just grind them up, add hot water, and drink.
Well, if only it were that simple. Unfortunately, the chaos is just beginning.
Oh, come on.
Seriously. Just as we have been completely fooled by the illusion of control with our roaster probes, we are currently being entirely fooled by the brewing devices sitting on our kitchen counters.
But brewing feels so simple. I use a French press every morning. I feel very much in control of that process. I weigh my coffee, I pour my water, I set a timer for 4 minutes, and I push the plunger down. I mean, it feels very tactile, very analog, and very precise.
I hate to break it to you, but traditional brewing methods, whether that is an immersion method like your French press or a percolation method like a fancy pour-over cone or even a highly expensive multi-boiler espresso machine, are fundamentally out of control physical systems.
Out of control? How could it be out of control? It's literally just hot water interacting with ground coffee.
To understand why it's out of control, we have to define what perfect control actually looks like.
Okay.
To get a mathematically perfect, maximally efficient, repeatable cup of coffee, every single individual particle of ground coffee needs to experience the exact same solvent, the water at the exact same temperature for the exact same amount of time.
Okay, that makes sense.
And in traditional brewing methods, because of fluid dynamics, that simply does not happen.
Okay, let's break that down mechanically. Why doesn't that happen in my French press? The water goes in, the coffee is in the water, they are all swimming together.
When you pour near boiling water over coffee grounds in a French press, microscopic chaos immediately ensues. First, you have to deal with trapped carbon dioxide.
From the roasting.
Right. The roasting process we just talked about created a massive amount of CO2, and much of it remains trapped inside the cellular structure of the bean. When you grind the coffee and hit it with hot water, that gas rapidly expands and is released. Millions of microscopic bubbles form.
Right. The coffee blooms, it bubbles up.
Exactly. But those bubbles act like tiny little life preservers. They physically attach to some of the coffee particles and float them rapidly to the top of the water column to form a dense, dry crust.
Well, the crust. Yeah, you usually take a spoon and just aggressively stir that back into the water.
You stir it, but it's a losing battle against buoyancy. And while half your coffee is floating in a crust, the other particles, the ones that didn't catch a CO2 life preserver, are instantly sinking to the absolute bottom of the glass to form a dense, muddy sludge.
Oh, right.
So within 10 seconds of pouring your water, you have coffee grounds experiencing entirely different extraction environments.
So the floaters at the top are physically exposed to the cooler ambient air of the kitchen.
Right.
Their temperature is dropping rapidly, and they are barely even touching the water solvent.
Correct.
And the sinker's at the bottom.
They are facing a completely different thermodynamic nightmare. They are trapped beneath a dense mountain of other sinking particles. The tiny amount of water trapped down in that dense sludge immediately pulls out soluble material from the coffee. Within seconds, that localized water becomes hypersaturated with coffee oils and acids.
Because the water down there is full. It physically cannot dissolve or hold any more solids. The solvent is maxed out.
Exactly. The extraction for the coffee at the bottom of the French press effectively halts. Add to that the random thermal convection currents happening in the middle of the glass as the hot water rises and the cooler water falls against the glass walls, creating entirely uneven fluid dynamics.
Wow.
The temperature of the entire system is dropping by the second. The extraction is totally heterogeneous. Some coffee is over-extracted, some is under-extracted, and none of it is controlled.
Okay, so immersion brewing like the French press is chaotic because gravity and CO2 separate the coffee. But what about percolation? What about pour-overs, where the water is constantly flowing through a bed of coffee?
Sure.
Or espresso, where we are actively using 9 bars of mechanical pressure to force water through the grounds? That has to be a more controlled physical environment.
Espresso is perhaps the ultimate illusion of culinary control. The machines look like precision laboratory equipment, but the mechanics inside the portafilter are incredibly messy. Yeah. Abbott has done extensive collaborative work with the Barista Hustle team on this exact problem, specifically analyzing the small, perforated metal filter baskets that hold the coffee in an espresso machine. They built a piece of digital analysis software called the Basket Hole Analysis app.
I absolutely love the methodology behind this. Let's unpack how this app works, because the steps required to use it highlight exactly why espresso is so chaotic at a microscopic level.
The premise of the app is simple, but the execution requires extreme precision to reveal the massive manufacturing inconsistencies in these metal baskets.
Okay.
The software requires you to take a high-resolution, perfectly backlit photograph of the bottom of your espresso basket. You crop the digital image exactly to the internal edge of the basket. You input the physical diameter into the software, say exactly 58 millimeters, and the computer vision algorithm counts and analyzes every single microscopic hole punched into that metal.
But those holes are incredibly tiny. I mean, they are fractions of a millimeter wide. How does a standard computer algorithm not just get completely confused by the reflections of the shiny metal or shadows inside the holes?
Abbott actually points out that designing the software was the easy part. Getting perfectly even lighting for the photograph is the hardest part. If you just hold it up to a window, the light bends and shadows distort the holes.
Right.
He recommends using a perfectly white laptop screen folded flat on a desk as a uniform backlight in a pitch-black room. Ideally, you want to use a collimated light beam.
Collimated light, meaning the light rays are perfectly parallel to each other rather than spreading out in a cone like a normal flashlight.
Exactly.
So the light goes straight up through the tiny holes without bouncing off the inner walls of the perforation, which would artificially widen the appearance of the hole in the photograph.
Exactly right. It requires scientific-grade photography just to get an accurate picture of a coffee filter.
That's dedication.
But once you have that perfect, shadow-free photograph, the app goes to work. And what it analyzes is highly revealing. We are looking for the total number of holes, the maximum diameter of the largest hole, the mean average size of the holes, the standard deviation of those sizes, and, crucially, the percentage of open area on the basket floor.
And what do you find when you run standard, highly expensive commercial espresso baskets through this analytical tool?
It's downright shocking.
Because these expensive precision machine pieces of metal aren't actually perfect at all.
Not even close. You might find a standard deviation that is wildly wide. Some holes might be 200 microns wide, while others right next to them are 300 microns wide.
That's a huge difference.
You will inevitably find blocked holes manufacturing defects where the metal punch didn't fully clear the steel, leaving a blind divot instead of a hole. Abbott notes that if you have 3 blocked holes out of a total of 1,000, that's 0.3%. A 0.3% blockage might not completely ruin your fluid dynamics, but what absolutely ruins the flow of an espresso is a metric called location variance.
Location variance, meaning the holes aren't spaced evenly across the bottom of the basket. There are microscopic gaps and clusters.
Right. To visualize this, the app creates a color-coded topological map of your basket. Green holes are perfectly average in their distance from their neighbors. Blue holes are clumped far too close together. Red holes are stranded far apart, surrounded by blank metal.
Okay, so if your holes are unevenly spaced, the high-pressure 9-bar water coming from your espresso machine will obey the fundamental laws of fluid dynamics.
Yeah.
It will instantly seek the path of least resistance.
Exactly.
So the pressurized water is going to bypass the red holes completely, and it's going to channel heavily through the clustered blue holes and the wider 300-micron holes.
Yes.
It's going to create microscopic geysers inside the coffee bed, violently over-extracting the coffee in those specific millimeter-wide zones, pulling out horrible bitter flavors while leaving the coffee sitting over the blank metal, completely dry and under-extracted.
It creates a chaotic channeling mess, and it gets even crazier when you look at the macro geometry of the total surface area. Abbott points out a classic pitfall in espresso mechanics. A barista might decide to switch their machine from a 54 millimeter wide basket to a slightly larger 56 millimeter basket. You might think, oh, it's just an increase of 2 millimeters. It's barely noticeable to the human eye. It won't change much.
But math says otherwise.
Drastically. If you keep the exact same dose of coffee, say 18 grams, that tiny 2 millimeter increase in diameter geometrically increases the total open area of the basket floor.
Because it's a circle.
Right. Because the area is wider, that same 18 grams of coffee now sits in a shallower, thinner bed. Because the bed is thinner and the area is wider, the fluid resistance drops and your flow rate increases by roughly 10%.
A 10% difference in extraction speed,
Yeah.
purely based on a 2 millimeter invisible difference in the metal geometry. And that's before we even talk about the thermodynamic nightmare of the machine itself. The water temperature drops the second it leaves the perfectly heated internal boiler. It hits the brass group head and loses heat. It hits the cold, dry coffee grounds and loses heat. It hits the ceramic mug and loses heat.
It is just constant heat loss.
It is a wildly uncontrolled thermodynamic and fluid dynamic channeling system wrapped in shiny chrome.
So we are left with a massive problem. If immersion brewing, like the French press, is chaotic because particles float and sink out of the solvent, and percolation methods like pour-overs and espresso are chaotic because water aggressively channels through uneven beds and microscopic manufacturing flaws,
Right.
how do we actually bring order to the universe of the coffee cup?
Enter uniform extraction, or UX, as Professor Abbott calls it.
Yes.
This is his absolute uncompromising answer to the chaos of modern brewing. So what exactly is uniform extraction?
Uniform extraction is a highly controlled, mathematically optimized method of immersion brewing. If our defined goal is for every single coffee particle to experience the exact same solvent at the exact same temperature for the exact same amount of time, we have to engineer a physical system that absolutely guarantees those conditions. We have to strip away the variables.
And how do we do that? Hearing all this talk of fluid dynamics and thermodynamic control, it sounds like I need to buy an incredibly expensive laboratory centrifuge.
It is surprisingly cheap and accessible, but it does borrow standard equipment directly from a chemistry lab.
Interesting.
First, to solve the massive problem of temperature loss during brewing, you don't use a ceramic mug or a plastic brewer. You use a double-walled borosilicate glass vessel. By putting a vacuum layer between the inner and outer glass walls, you virtually eliminate conductive heat loss.
Okay, so it's a thermos, basically.
Exactly. The water goes in at your exact target temperature, and it stays at that exact target temperature for the entire duration of the 2-minute brew.
Okay, thermodynamic temperature control is solved by the vacuum glass. But what about the fluid dynamics? What about the CO2 bubbles floating half the coffee into a crust and gravity sinking the other half into a hypersaturated sludge? How do we defeat gravity and buoyancy?
To solve the fluid dynamics, you borrow a magnetic stirrer from the chemistry lab.
A magnetic stirrer.
You drop a small Teflon-coated magnetic bar, often called a flea, into the bottom of the glass vessel. You place the vessel on an electronic stirring plate, and you dial in a precise digital rotation speed.
I remember seeing these exact tools in high school chemistry class. It's just a little white pill-shaped magnet spinning furiously at the bottom of a beaker of liquid.
Exactly. When you spin that magnetic bar at a digitally controlled speed, say 800 or 1200 revolutions per minute, you create a perfect, sustained, powerful fluid vortex in the water.
Wow.
The centrifugal force and the downward pull of the vortex are significantly stronger than the buoyancy of the microscopic CO2 bubbles. There is no crust. The continuous uplift from the turbulent eddies completely overpowers gravity. There is no sludge.
That's amazing.
Every single particle of coffee is held in a constant, mathematically homogeneous suspension. They are flying through the water, physically separated from one another, experiencing the exact same extraction environment.
Okay, but here's where it gets really interesting to me. We aren't just spinning the water to keep the coffee particles suspended so they don't form a crust. The physical act of stirring violently alters the chemistry of the extraction itself at a microscopic level. It actually changes how the flavor leaves the bean.
Yes. If we connect this to the bigger picture of fluid mechanics and physical chemistry, we have to talk about a concept called the mass transfer coefficient. And this goes back to an analogy that perfectly visualizes what is happening on a microscopic scale.
The sugar in the iced tea.
Yeah.
I absolutely love this analogy because it instantly clarifies the physics.
It's perfect.
If you have a tall glass of cold iced tea and you drop a solid sugar cube into it, and you do absolutely nothing, you don't stir it, you just watch it.
Yeah.
What happens? The sugar cube just sits at the bottom of the glass. It doesn't dissolve. And the physics explain why. The very thin, microscopic layer of water that is physically touching the surface of the sugar cube dissolves a tiny bit of sugar almost instantly. But then, that localized microscopic layer of water becomes totally saturated. It physically cannot absorb a single additional molecule of sugar. It becomes a thick, localized syrup hugging the cube.
And because the tea is cold, there are no thermal convection currents to move that heavy syrup away.
Right. The sugar cube is effectively trapped inside its own saturated boundary layer.
And the only way the rest of the sugar inside the cube can dissolve into the rest of the glass is through the incredibly slow, passive diffusion of those sugar molecules migrating outward into the wider body of water.
Which would take hours.
Exactly. But if you take a spoon and stir that glass of iced tea violently,
You physically rip that saturated syrup layer away from the surface of the sugar cube. You use mechanical force to constantly slam fresh, completely unsaturated water against the surface of the sugar. And as a result, the sugar cube dissolves into the cold tea almost instantly.
and that is exactly, mechanically, what the magnetic stir is doing to the suspended coffee grounds inside the uniform extraction vessel. It is inducing a highly turbulent fluid flow right at the microscopic boundary, where the water solvent meets the solid cellulose structure of the roasted bean.
That makes total sense.
But in maintaining a 1200 RPM vortex, you are forcibly, continuously ripping away the saturated boundary layer of coffee oils and acids. You are dramatically accelerating the mass transfer coefficient.
So the logic is clear. Faster stirring means faster extraction because you are constantly supplying fresh solvent to the surface of the bean.
Yes, but crucially, it is not a one-to-one linear relationship.
Oh, really?
Abbott relies on heavily validated mathematical theory from chemical engineering papers published by researchers Moroney and Wang to show that the extraction rate actually scales with the square root of the RPM.
The square root. Okay, let's do the math on that so we understand exactly how much control we actually have.
If your default digital stirring speed on your magnetic plate is set to 800 RPM, and you decide you want to radically double the turbulent mass transfer effect to extract the coffee twice as fast, you logically might think, I'll just turn the dial up to 1600 RPM.
Yeah, double the speed, double the flavor.
But doubling the motor speed from 800 to 1600 does not double the extraction rate. It only increases the rate by the square root of 2.
And the square root of 2 is roughly 1.4. So physically doubling the speed of the motor and creating a wildly violent vortex only gives you a 1.4 times increase in the actual extraction rate.
Correct. It represents a diminishing return on mechanical energy. But that 1.4 times multiplier is incredibly significant when you are a barista trying to precisely, perfectly dial in a strict 2-minute brew time, because you now have total mathematical control over the turbulence variable.
Okay, so let's check our variables. We have perfect thermodynamic temperature control with the vacuum-sealed double-walled glass. We have perfect fluid dynamic suspension and mass transfer control with a magnetic stir inducing turbulent flow. But we still need to know, how fast is the coffee flavor actually dissolving into the water? Because the flavor compounds don't just dissolve at a perfectly steady pace for 2 minutes and then suddenly stop, right?
Right. And to understand the velocity of flavor, we have to look at the underlying mathematical architecture of extraction.
Okay.
In Professor Abbott's chemical extraction models, the process of extracting roasted coffee mass up to its maximum theoretical total dissolved solids, which the industry calls TDS, follows a very specific, well-documented mathematical curve called a Weibull curve, W-E-I-B-U-L-L.
The Weibull curve.
Ah.
I know that's used heavily in engineering to measure particle size distribution and even product failure rates. What does it look like in practice when applied to coffee flavor?
The Weibull formula relies heavily on a rate constant, represented mathematically by the letter K, and a shape parameter, represented by the Greek letter beta. When modeling the extraction of coffee into water, beta is surprisingly consistent. It is usually a constant shape set right around 0.7. What this specific curve visually dictates on a graph is that extraction does not happen on a straight, linear, 45-degree diagonal line. You do not get a linear return on your brewing time.
Meaning, if I brew my coffee for 1 minute, I don't get exactly 50% of the total available flavor, and then at 2 minutes I get exactly 100%.
Not at all. The Weibull curve dictates that extraction is incredibly aggressively front-loaded. It starts almost instantly.
Wow, okay.
Well over 50% of your total possible extraction, the mass leaving the bean and entering the water, happens in the very early initial seconds of the brew. Then, the mathematical curve violently tapers off, rounding the corner and becoming almost entirely flat and horizontal.
So the extraction basically stops.
Exactly. Once you hit that flat part of the curve, you could double your physical brew time from 4 minutes to 8 minutes, and you might only increase your actual extraction by a microscopic fraction of a percent.
Because all the easily accessible, highly soluble material located on the exterior of the grounds has already been aggressively ripped out by the turbulent flow of the vortex in the first 30 seconds.
You've got it.
You are just leaving the coffee spinning in the water, waiting for the deepest, most dense, most stubborn molecules to slowly, passively diffuse out of the absolute center core of the cellular particles.
Yes, and the speed of this entire Weibull curve, that fundamental rate constant K, is heavily influenced by our old friend temperature. But the way thermal energy actually affects coffee extraction is incredibly surprising, and Abbott uses a concept called the Arrhenius activation energy to explain exactly why.
The Arrhenius equation. This is a foundational formula in physical chemistry that calculates exactly how much thermal energy is required to kickstart a specific chemical reaction.
Right. It measures the thermal barrier to entry. And what the research by Wang discovered is that the Arrhenius activation energy required for coffee extraction is shockingly incredibly low. It is only about 16 kilojoules per mole. To put that in culinary perspective, the activation energy required to caramelize sugar in a pan is vastly higher.
16 kilojoules per mole.
Okay.
Which sounds like a tiny number.
Yeah.
What does that mean in practical terms for the listener standing in their kitchen?
It means that you fundamentally do not need near boiling water to extract the physical mass from roasted coffee. Because the chemical activation energy required to pull those solids into solution is so low, cold water still works incredibly well at pulling out total dissolved solids.
Okay, I'm listening.
If we use 93 degrees Celsius just off the boil as our optimal baseline, representing a 100% extraction rate, if you drop the water temperature down to 50 degrees Celsius, the extraction rate doesn't plummet to zero. It is still humming along at 50% of the maximum rate.
Wow.
Even if you use water straight from the tap at room temperature, around 23 degrees Celsius, the extraction rate is still a massive 30% of what it is near boiling.
Wait a minute. Okay, let me push back on this because this feels like a contradiction.
Let's hear it.
If cold water sitting at room temperature extracts physical mass 30% as fast as nearly boiling water, why do we bother boiling water at all? Why doesn't a glass of cold brew coffee taste absolutely identical to a hot cup of coffee, assuming you just leave the cold brew steeping for roughly 3 times as long to make up for the 30% speed difference?
That is a brilliant pushback. And the answer lies in understanding the critical difference between total dissolved solids, which is purely a measure of blind physical mass and complex human sensory chemistry.
Okay, so the digital refractometer measuring TDS only measures the total mass floating in the water, but the human tongue measures the specific individual flavor compounds.
Precisely. You could use a refractometer and find that a batch of room temperature cold brew that's steeped for 12 hours has an exact TDS of 1.4%. And your hot uniform extraction brew that's steeped for 2 minutes also has an exact TDS of 1.4%. They have perfect mass parity.
But they taste different.
Very different. Because what exact chemical molecules comprise that 1.4% mass? Caffeine, for instance, is highly soluble regardless of temperature. It dissolves easily in cold water, so cold brew is fantastic at extracting a massive dose of caffeine.
Right.
But roasted coffee contains thousands of complex aromatic oils, highly volatile organic compounds, and specific delicate organic acids that have uniquely different individual solubility thresholds.
Ah, I see. So there are certain beautiful, floral, bright, acidic flavor compounds locked deep inside the cellulose of the bean that simply will not break their chemical bonds and enter the water unless they're violently smashed with the high thermal kinetic energy of 93-degree water.
Exactly. If you brew with cold water, you will eventually reach your target mass of 1.4% TDS, but you're leaving all the high-energy, delicate aromatic oils behind in the grounds.
That makes sense.
And worse, to reach that 1.4% mass, you end up over-extracting the heavier, lower-energy, harshly bitter chemical compounds that dissolve very easily in cold water. You achieve mathematical mass parity, but you completely fail to achieve chemical flavor parity.
That is utterly fascinating. So the Weibull curve dictates the speed of the mass extraction, but the thermal Arrhenius energy dictates the quality and chemical makeup of that mass.
You nailed it.
Okay, but there is one massive glaring variable in the Weibull equation we haven't touched on yet. We've talked deeply about temperature. We've talked about turbulent fluid flow. What about the physical size of the coffee grounds themselves?
Grind size is perhaps the single most critical geometric factor dictating that extraction rate, constant K. And the speed at which a particle extracts based on its size is governed by a standard, completely immutable law of physics, the inverse square law of diffusion.
The inverse square law. Okay, let's unpack this slowly. Because when I read Professor Abbott's notes on this specific math, it completely blew my mind and changed how I look at my grinder.
It's revolutionary. The physical law states that the rate of chemical extraction depends inversely on the square of the particle's diameter.
Yep.
Let's look at a highly practical microscopic example. Let's say you grind some coffee, and you have a relatively large particle of ground coffee, what we call a boulder, that is exactly 650 microns in diameter.
Okay, 650 micron boulder.
And sitting right next to it in the water, you have a tiny microscopic speck of coffee dust, what we call a fine, that is only 100 microns in diameter.
Okay, so the large boulder particle is mathematically 6.5 times wider than the microscopic fine.
Right. But because of the inverse square law of diffusion, you don't just divide the extraction time by 6.5, you divide it by 6.5 squared.
And 6.5 times 6.5 is roughly 42.
Exactly. Because of its geometric size, that tiny 100 micron fine will extract its soluble mass 42 times faster than the 650 micron boulder sitting right next to it.
42 times faster. That is an unbelievable discrepancy in a single cup of coffee.
Yes. And because we already know that the Weibull curve dictates that coffee extraction is massively front-loaded, when you apply a 42 times speed multiplier to a 100 micron particle and you place it inside a highly turbulent 1200 RPM magnetic vortex,
Yeah.
the extraction of that microscopic fine is, for all intents and purposes, instantaneous.
Instantaneous.
The absolute millisecond that 93-degree hot water touches a 100 micron coffee fine, 100% of its soluble flavor is violently and immediately ripped out into the surrounding liquid.
Which means, logically, you cannot prevent fines from fully extracting. It is a physical impossibility.
Impossible.
If you have any microscopic dust in your grinder output, those fines will instantly contribute absolutely everything they have, the good flavors and the harsh, bitter, over-extracted flavors to the cup, regardless of whether your total brew time is 1 minute or 2 minutes or 10 minutes.
Exactly. The fines are a mathematical absolute, and it gets geometrically even more complex.
Really? How?
Well, you might hear this and think, okay, the solution is simple. I will just spend $3,000 on a massive, perfectly aligned commercial flat burr grinder, and I will mathematically eliminate all the fines. I will only brew with perfectly uniform 650 micron boulders. That will slow the extraction down.
That seems logical.
But even those massive boulders extract incredibly fast in the initial seconds. Why? Because of fractured surface area.
Fractures. Because grinding a brittle, roasted coffee bean isn't like slicing a soft carrot with a razor-sharp scalpel. It's an inherently violent process. It's like taking a hammer and smashing a piece of slate rock.
Precisely. A mechanical grinder violently shatters the brittle, carbonized structure of the roasted bean. And when you look at one of those 650 micron boulders under a high-powered scanning electron microscope, its surface is not perfectly round and smooth like a polished billiard ball.
It's rough.
Very rough. The entire exterior is covered in jagged microscopic ravines, craters, and deep cellular microfractures.
And obviously the hot water solvent can easily penetrate inside those deep ravines.
Yes, and Abbott calculates the geometry of this beautifully. If those microscopic fractures go just 20 to 30 microns deep into the rough surface of that 650 micron boulder, that seemingly tiny microscopic exterior surface layer actually mathematically contains roughly 17% to 25% of the particle's entire total physical volume.
Wow. A full quarter of the total volume of this massive boulder is physically exposed right at the immediate surface due to these jagged microfractures.
And what happens to completely exposed volume when you submerge it in a highly turbulent 93-degree mass transfer environment?
It extracts almost instantly.
Exactly.
Yeah.
So when you combine the instantaneous, unavoidable extraction of the microscopic fines with the rapid, violent extraction of the microfractured outer layers of the massive boulders,
You begin to see exactly why over 50% of the total coffee extraction in the Weibull curve happens almost the very instant the water touches the beans.
This raises an important question, though. How do we even know what our exact grind size actually is? Because every time I turn the dial on my home grinder, I don't see microns. I just see a messy pile of dust and chunks. How do I actually know if I have a 650 micron boulder or a 100 micron fine?
This is where Professor Abbott developed another absolutely brilliant, accessible piece of digital software, the grind size analysis tool. He notes it was heavily inspired by the astronomical image analysis work of astrophysicist Dr. Jonathan Ganya.
Oh, wow.
The entire premise is to use your smartphone camera to mathematically quantify the mechanical chaos of your burr grinder.
Okay, walk me through the user experience of this tool. I have my messy pile of freshly ground coffee on my kitchen counter. What exactly do I do?
First, you take a highly controlled, backlit photograph of a very small, sparse sprinkling of your coffee grinds. Again, utilizing the bright white screen of a laptop laid completely flat on a table works perfectly as a light source.
Got it.
Crucially, you have to place a physical ruler or a millimeter scale in the frame of the photograph, so the software algorithm have a hard, real-world calibration reference. For example, you measure the image and tell the app, the exact physical width of this image from edge to edge is exactly 138 millimeters.
Okay, so the computer algorithm now understands the physical scale of the pixels. But how does it isolate the coffee from the background?
It uses digital image processing thresholding. You manually set a min pixels and max pixels slider limit to filter out digital sensor noise or random specks of dust on your camera lens. But the absolute key to the algorithm is the color thresholding. Abbott highly suggests utilizing the blue channel of the standard RGB digital color spectrum.
The blue channel. Why not just use black and white or grayscale?
Because of the specific color theory of roasted coffee. Roasted coffee is essentially a dark brownish orange. Orange is a combination of red and green light. Therefore, the blue channel is the exact mathematical inverse of the coffee's color.
Oh, that's smart.
By isolating just the blue channel data in the photograph, the software creates the maximum possible visual contrast between the brown coffee particles and the bright white backlight. Anything darker than your specific blue threshold is mathematically defined by the computer as a solid blob or discrete particle.
So the computer algorithm rapidly identifies and counts thousands of these individual dark blobs, calculates their total pixel area, and uses geometry to calculate their physical radius in microns.
Yes, and here's where we hit the true genius of the app, and the moment that completely rewired my brain regarding coffee extraction. The app forces you to visually and mathematically confront the massive difference between number and volume.
Okay, explain that.
Let's use a hypothetical situation to explain this. You run the app, and the algorithm finds exactly 100 individual particles of coffee in your photograph. 99 of those particles are microscopic fines. Let's call them size 1. And one single particle in the frame is a massive, jagged boulder. Let's call it size 100.
Okay, so if I look at a standard bar graph representing the number of particles, it looks like my grinder produced an output that is 99% fines. I might look at that and think I have a super fine, powdery espresso grind.
But that graph is a complete total illusion.
Right.
Because chemical extraction into water is not driven by the mere number of particles. 100 tiny specks don't equal one giant boulder. Extraction is driven by mass, and mass is a direct function of volume. And the geometric formula for volume dictates that it scales with the diameter cubed.
Ah, I see the math unfolding here. So the total volume of a single size 1 fine is just 1 cubed, which is still just 1. So the total combined volume of all 99 of those microscopic fines put together is exactly 99.
Exactly. But let's calculate the volume of that one single lonely size 100 boulder. 100 cubed is 1 million.
Good grief, so that one single boulder is literally 1 million times larger in volume than a single fine.
Yes. So if you look at your grind by number, it is 99% fine dust. But if you look at it by physical volume, those 99 fines are mathematically insignificant. They barely exist. That single massive boulder contains 99.9% of the actual physical mass of the coffee.
That's insane.
It will entirely, completely dominate the flavor extraction process. If you, as a barista, do not understand the fundamental mathematical difference between particle volume and particle number, you will never, ever understand why your coffee tastes sour or bitter.
Because the millions of microscopic fines instantly gave up all their harsh, bitter, over-extracted flavors the millisecond the water hit them. But that one massive boulder, which contains all the actual mass, is going to take several minutes to fully extract, leaving the vast bulk of the liquid solvent totally under-extracted and sharply sour. You have engineered a beautiful, chaotic symphony of terrible, conflicting flavors.
Exactly. And the Grind Size app visualizes this reality perfectly. You can look at the number graph on your screen and see a massive, towering mountain of fine dust.
Yeah.
But then you click a button to switch over to the volume graph, and that mountain of dust completely disappears, replaced by a massive, towering spike on the far right side of the screen at the bolder end of the spectrum. It strips away the visual illusion and reveals the true physical, geometric reality of your coffee grounds.
Okay, my mind is thoroughly, completely blown. We have systematically deconstructed the lies our Spencer Roaster probes tell us. We have mathematically exposed the chaotic channeling of pressurized espresso baskets. We have geometrically proved that fines extract instantly at 42 times the speed of boulders. And we've established that magnetic stirring in a vacuum glass gives us total mathematical control over the mass transfer coefficient.
It's a lot.
So, taking all of this high-level physics, how do we practically put this all together in our kitchen tomorrow morning? How do I physically build a uniform extraction rig without bankrupting myself?
It is shockingly, wonderfully accessible. You absolutely do not need to buy a $3,000 piece of specialized coffee equipment.
Good to hear.
You go online to a scientific supply store and you buy a cheap digital magnetic stirrer. It will cost you roughly 30 to 40 British pounds, or about 50 US dollars. Crucially, you do not need an expensive combination hot plate stirrer because hot plates create thermal convection chaos. You just need the motorized stirrer base.
It's the stirrer.
You also buy a standard 3-centimeter Teflon-coated magnetic stirrer bar. The Teflon coating ensures it doesn't react chemically with the acidic coffee. Finally, you buy a double-walled borosilicate glass vessel with a lid. Brands like Doppler or EcoBrew make perfect vacuum-insulated glass flasks.
Okay, I have my mad scientist laboratory equipment assembled on my kitchen counter. What is the actual optimized uniform extraction recipe?
You start with a standard mathematically sound brew ratio, 15 grams of medium ground coffee. You take 250 milliliters of near boiling water, say 93 degrees Celsius, and you pour it directly into the preheated glass vessel.
Okay.
You drop the 3-centimeter magnetic stirrer bar in, and you turn the digital dial on the base plate until you establish a clean, powerful, unbroken vortex pulling down to the bottom of the glass at exactly 1200 RPM.
The water is spinning furiously, creating maximum turbulence.
Then you tip your 15 grams of dry coffee directly into the center of that spinning vortex, and you immediately start a digital timer.
And instantly, because of the massive turbulent kinetic energy of the water, we are violently ripping away those saturated boundary layers. The microscopic fines extract instantaneously, and the jagged, microfractured exterior surfaces of the 650-micron boulders rapidly give up their payload into the solvent.
Exactly. You let it spin and stir in total, mathematically homogeneous control for exactly 2 minutes. Every particle gets the exact same temperature, the exact same solvent, the exact same turbulence. Then, right at the 2-minute mark, you click the stirrer off.
Okay, the magnetic field stops, the physical vortex collapses. Now we just have a glass full of turbulent, dark, muddy water filled with floating coffee grounds. We obviously can't drink that. We have to somehow physically separate the solid coffee grounds from the liquid solvent, but we can't use a paper filter because that would absorb the delicate aromatic oils we just worked so hard to extract.
This brings us to a new physics problem. How do we separate them? And the solution is the final and perhaps most beautifully elegant application of physics in the entire UX process, the settling phase.
The settling phase.
When the motorized stirrer stops, you simply walk away and wait for exactly 3 minutes. And what governs this separation phase is a foundational principle of fluid dynamics called Stokes' law.
Stokes' law! This is brilliant. How exactly does Stokes' equation dictate our coffee grounds settling to the bottom of the glass?
We have to look at the specific variables within the Stokes equation. The terminal velocity of a falling spherical particle, meaning exactly how fast it sinks down through the water to the bottom of the glass, equals a constant, roughly 0.545, multiplied by the specific difference in density between the solid particle and the liquid solvent times the acceleration of gravity times the square of the particle's diameter, all divided by the physical viscosity of the liquid.
Okay, let me visualize the mechanics of that equation. So the physical difference in density between the solid coffee particle and the water it's floating in is the primary engine actually driving the fall downward against the fluid resistance.
Exactly. If the coffee particle somehow had the exact same density as the water, that density term in the equation becomes zero. The entire velocity becomes zero. It would just hover there, perfectly weightless, forever.
Right.
And here is where the cellular structure of coffee gets absolutely fascinating. The intense roasting process we talked about earlier physically puffs up the beans. When they undergo first crack and release steam, the cellular matrix expands violently, trapping microscopic pockets of air.
Right, so a very dark roast, which has been subjected to more heat and has expanded significantly more, is mathematically much less dense than a light roast.
Yes, a typical dark roast coffee bean might have an overall density of around 1.05 grams per cubic centimeter. It is barely denser than water, which is 1.20. A medium roast is slightly denser, around 1.1 grams per cubic centimeter. A highly dense light roast, which hasn't expanded nearly as much during roasting, is up around 1.2.
And because that critical difference in density is the primary engine driving the Stokes equation, dense, heavy light roasts are going to physically fall and settle much faster through the water column than light, airy, dark roasts.
In fact, as a general mathematical rule of thumb, for each of those density steps from dark to medium to light, the physical settling speed effectively doubles. Light roasts are twice as fast to settle out of the liquid as medium roasts, which are twice as fast as dark roasts.
That's amazing.
Light roasts are significantly easier to clarify. Furthermore, we have to look at the other massive variable in Stokes' law, the square of the particle's diameter.
The inverse square law strikes again, but this time it's working in reverse to help us.
Yes, geometrically larger particles settle much, much faster. The math states that if you have the physical diameter size of a particle, it actually falls 4 times slower through the fluid. So those massive, heavy 650-micron boulders plummet rapidly to the bottom of the glass like stones.
But those tiny 100-micron fines we talked about.
Because they are roughly 6.5 times smaller in diameter, the math dictates they will settle over 40 times slower. A microscopic fine might effectively never settle out of the liquid in any reasonable human time frame. It will just hang suspended in the fluid indefinitely, causing cloudiness.
And wait, there's another massive fluid dynamic complication here, right? Because the Stokes equation assumes a single solitary particle falling freely in an infinite body of fluid. But in our uniform extraction vessel, we don't have one particle. We have millions of colliding particles. As the heavy boulders fall rapidly toward the bottom, they must start to bunch up. They create physical traffic.
Yes, the particles create massive drag on one another. Abbott uses the Richardson and Zaki approximation formula to mathematically model this specific phenomenon, known as hindered settling.
Hindered settling.
It states that the falling velocity of any individual particle is drastically reduced by a mathematical factor directly related to the local volumetric concentration of the other surrounding particles. As the boulders gather at the bottom of the glass, the local concentration spikes wildly, and the settling rate across the board drastically, painfully slows down. The water at the bottom of the glass becomes a dense, inescapable traffic jam of colliding, turbulent particles.
So if the heavy boulders are constantly causing a dense traffic jam at the bottom, and the microscopic fines are completely defying gravity because they are 40 times too small to sink, how do we ever actually get a clean, clear cup of coffee? We only have a 3-minute timer running.
Here's where it gets really interesting, and this is my absolute favorite part of the entire uniform extraction process.
Okay.
You don't just turn off the stirrer and let the glass sit flat and vertical on the kitchen counter. You physically tilt the entire glass. You utilize a brilliant phenomenon known in complex fluid mechanics as the boycott effect.
The boycott effect. I am vaguely familiar with this from hematology, actually.
Yes. In the 1920s, a brilliant medical researcher named Arthur Boycott was exhaustively studying the sedimentation rate of red blood cells in laboratory test tubes. He noticed a bizarre anomaly.
What was it?
If he put blood in a perfectly vertical test tube, the red blood cells took an incredibly long time to fully settle to the bottom. But if he accidentally left the test tube leaning sideways at an angle in the rack,
The red blood cells settled out of the plasma incredibly fast.
drastically, exponentially faster. And the physics behind why this happens are absolutely beautiful. When heavy coffee grounds or dense red blood cells fall downward in a perfectly vertical tube, they displace water.
Right.
That displaced water has to go somewhere, so it is forced to push straight upward, directly through the massive dense cloud of falling particles. This upward flow of displaced water creates massive turbulent drag, actively fighting against gravity and holding the falling particles up.
The falling boulders are essentially fighting head-on against a rising tide of their own displaced water.
Exactly. But if you physically tilt the brewing glass at a 30 to 45 degree angle,
Yeah.
the heavy falling particles don't have to fall all the way down to the absolute bottom of the glass. They only have to fall a few short millimeters vertically until they hit the downward sloping lower wall of the tilted glass.
Oh, wow.
Once they hit that solid glass wall, they slide rapidly and smoothly down the incline to the bottom corner, completely out of the main vertical fluid column.
And what happens to all the water that is being displaced?
Because the massive clump of particles is sliding tightly down the lower sloped wall, they leave a perfectly clear, completely particle-free, unobstructed channel of pure liquid resting against the upper sloped wall of the glass.
Oh, that's brilliant.
The displaced solvent, the water, escapes rapidly and cleanly up this clear back channel. It completely, entirely bypasses the falling particles. The upward fluid drag is totally eliminated. The overall settling process speeds up exponentially.
It is so incredibly deeply satisfying to use advanced fluid dynamics and 1920s medical blood settling physics to simply make your morning cup of coffee. You literally just tilt your double-walled glass at a 45-degree angle, wait exactly 3 minutes, and watch this brilliant, invisible fluid dynamic conveyor belt silently separate your coffee from your water for you.
It really is. And once that 3-minute boycott settling phase is complete, all the dense boulders are densely packed at the very bottom corner of the angled glass. The perfectly clear, deeply colored liquid is sitting pristine on top.
Incredible.
You simply pour the clear liquid gently through a very fine metal tea strainer just to catch any of those stubborn microscopic fines that refuse to settle out, leaving the thick, over-extracted sludge trapped safely behind in the glass.
And what you are left holding in your mug is a mathematically perfect, uniform extraction brew. A cup of coffee where absolutely every single variable, the thermodynamics of the temperature, the fluid dynamic turbulence, the chemical mass transfer coefficient, the physical geometry of the grind, and the terminal velocity of the settling phase was strictly mathematically controlled.
There is no barista mysticism. There is no guessing. Just pure, unapologetic, repeatable physics.
It is a fundamentally radically different approach to a daily ritual that most of us just sleepwalk through.
It truly is. So let's quickly recap this wild, incredibly dense journey we've just taken. We started by realizing that the highly expensive blinking screens on our commercial coffee roasters are largely feeding us complete illusions, entirely driven by the thermal inertia of heavy metal probes.
Right.
We learned that tumbling drum roasting is an ill-posed mathematical problem that is best solved not by frantic micromanagement, but by letting go of control and utilizing a mathematically calculated two-step heat drop to ride the exothermic first crack.
We looked microscopically at fancy espresso machine baskets and realized that a completely invisible 2-millimeter difference in a piece of stamped metal can radically, violently alter our extraction fluid dynamics through location variance and high-pressure channeling.
We deeply uncovered the inverse square law of grind size geometry, proving mathematically that microscopic fines will instantaneously, violently give up all their flavor. The exact millisecond hot water touches them, while the deep, fractured exterior surfaces of massive boulders give up a quarter of their volume just as aggressively fast.
And we finally took ultimate, total control of this inherently chaotic physical system by using a cheap magnetic stirrer in a vacuum glass to mathematically dictate the mass transfer coefficient via the exact square root of the RPM, followed by utilizing the brilliant medical physics of the boycott effect to rapidly settle the coffee grounds using an angled clear water back channel.
Yeah, it is a massive amount of high-level physics to process for a single cup of coffee.
It absolutely is.
Yeah.
But I want to leave you with one final, broader thought to mull over long after you finish listening.
What's that?
Well, we just spent a full hour mathematically rigorously proving that something as ubiquitous, as commonplace, and as heavily scrutinized as making a simple morning cup of coffee has been largely out of control for centuries. We've been completely blindly governed by complex fluid dynamics, shifting thermal inertia, and unforgiving thermodynamics that we barely even acknowledged existed, constantly substituting real hard physics for vague concepts of feel and art.
That's so true.
It makes you wonder. What other daily, seemingly mastered culinary rituals occurring in your kitchen right now are completely scientifically uncontrolled, just waiting for their own uniform extraction revolution?
Are we baking our bread fundamentally wrong? Are we searing our steaks using entirely flawed thermodynamic assumptions?
Exactly.
It's a terrifying but ultimately thrilling thought for anyone who loves the science of food. Thank you for joining us on this incredibly dense, mathematically rigorous deep dive. The next time you press down on the plunger of that French press or watch your shiny espresso machine sputter and channel, just remember, the immutable laws of physics are always there, humming beneath the surface, just waiting for you to stop guessing and finally take control. Until next time, keep questioning the physics of the everyday world.